Hi, this is Ana Doblas. In today's video, we're gonna solve 4 multi-choice questions regarding module number 5, electromagnetic optics. So the first multi-choice question is regarding, consider that we have an electric and magnetic field. Both of them are vectorial fields, and then we need to select the correct pointing vector. We know that the pointing vector, it can be expressed as capital S, and this is going to be the product, the cross product between the electric field and the magnetic field. So let me use the whole screen. So this is going to be the cross product between the electric field and the magnetic field. We are assuming that both fields are expressed in Cartesian coordinates. And then here we're going to have 1, 2, 3, and then 3, 2, 1. So the first thing that we're going to have is we're going to have x2 plus 9 plus 9y plus 2c, and now we are going to the other side, so we're gonna have the negative minus 6 along the c direction minus y, and then we're gonna have minus 6x. So we can combine all of them together. So we're gonna have minus 4x plus 8 along the y direction minus 4 along the z direction. So if we express them, then our pointing vector is going to be minus 4, 8, minus 4. So this is clear, our B option of the problem. Alright, so the second problem that we are solving today is that we know that we need to estimate the electric susceptibility of the water. So if you remember, and we are saying that the system needs to be considered only having electric properties, so that means that, that means that the magnetic permeability is the one from the vacuum, but then what we're gonna have is that the electric is equal to the electric permittivity and then 1 plus R susceptibility. So this is the information that we need to know. So we know that the refractive index is the ratio of the light at the vacuum, that's the universal constant, divided the speed in the medium, which is going to be water. So the speeds are 1 over the square root. Here is going to be in the vacuum, and 1 over in the medium, that is going to be water, but does not have electric magnetic properties. So this is going to be the electric permittivity in the water divided the electric permittivity in the vacuum of the air square root, knowing that the electric permittivity is like the one from the vacuum, 1 plus the susceptibility. This is going to be equal to 1 plus R susceptibility. And this is only going to be true because we have considered that the medium is going to be linear, non-dispersive, homogeneous, and isotropic. Alright, so we know that the refractive index is the square root of 1 plus the susceptibility. So the square of the refractive index is 1 plus the susceptibility. So the susceptibility is equal to the refractive index squared minus 1. So if we insert the one from the water, we're gonna find out that our susceptibility is 0.7689, and that means that the correct solution is gonna be B. So the next problem, they telling us this is about Beer's law. So they tell us that we have a medium. So we know that we have a medium here. And we know its absorption coefficient, right? So if you remember the Beer's law is telling us that the intensity after the light travels a medium it's gonna be our incident intensity, the exponential of minus alpha x, where x is the thickness of the medium, right? So alpha is gonna be our absorption coefficient. And then delta, which is what it's asking us, it's our penetration depth, which is the inverse. This is gonna be our penetration depth. And now if we do that, we know that alpha is gonna be 0.05 inverse of the meter. We have the penetration depth is gonna be 20. So that means that the correct answer is gonna be A. And I want you to remember that D, it's a physical distance. In which the intensity is reduced by a factor of A. So this is how much we need to move away, or how thick the material needs to be, so there is a drop of the intensity by the factor of A. The next problem is similar. It's still the Beer's law, but it's gonna be generalized, since we have an incident light going into a material, and the problem telling us that the intensity of the light is reduced by half. So our intensity is reduced by half. And in our medium, we have absorption and scattering. So this is the difference here. So we have absorption. So we know that the absorption coefficient is gonna be 0.025 inverse of the centimeters, but we also have scattering. And they are asking us how much is the scattering coefficient. Alright, so remember that this is gonna be now our generalized Beer's law. So we have here that our final intensity is equal to our incident intensity, the exponential of. And now here what we're gonna have is our absorption. Let me use colors. So we have here our absorption coefficient plus our scattering coefficient, and then with our thickness. And then we know that the thickness of the material is 0. This is gonna be 0.05 meters. All right, so if there is a drop of intensity half, so we're gonna have here 1.5, the exponential of minus. Here we have the sum of the coefficients, the absorption and the scattering, and then we have like the natural logarithmic of 1/2 equal minus x, the sum of our coefficients. Now that minus we can invert it, so we have natural logarithmic of 2 divided the x. This is gonna be the summation of our coefficients, the absorption and the scattering. So at the end, my scattering coefficient, that's gonna be natural logarithmic of 2 over how thick the material is minus our coefficient, absorption coefficient. So now here what we need to be careful is about this pouring everything on the same unit. So we have 0.025 inverse of centimeters. So I'm gonna write, or we should write x as, it says 0.05 meters. So we need to write it better as 5 centimeters. Therefore, our scattering coefficient is gonna be equal to 0.1136 inverse of the centimeters. And that makes that our current solution is gonna be the C option. So I hope that those videos help you understanding the concepts of module number 5. Thank you.